Wataru IShizaki. It's contributing talk.
Good afternoon, everyone. I'm Wataru IShizaki from Yukon Institute for Theoretical Physics, Kyoto University. A collaborator of this work is Kunihito Yuka-san. He will give a talk next and may talk related my topics. Okay, today I will give a talk about the stability analysis of Alfven wave motivated from the FRB emission mechanism modeling. Okay, let's start. Okay, first I will introduce FRB. Maybe almost all participants know well, so I give a just brief introduction. The FRB is a transient phenomenon in the regular bands, and its typical flux is or the Jansky gigahertz band, and typical duration is millisecond. And the distance from the source to the source from Earth is estimated from the dispersion measure, and the value of dispersion measure clearly indicates the source of FRB is cosmological and at the cosmological distance. Combining these values, we can estimate the brightness temperature, and we can estimate the brightness temperature, and it indicates the FRB emission mechanism of FRB is some coherent process. So the FRB source of mechanism of FRB is still unknown, but some hints we have some hints. For example, short duration means maybe the source is compact structure, or since there are repeating species. Repeater, so the source may be the cataclysmic origins may be difficult, and most important observation is I think is SGR 1935. It's magnetic sphere of magnetized is a source, promising candidate of source of FRB. Okay, as the title of my talk suggests, today I will talk about, of course, Alfven waves. Alfven waves in the magnetic sphere have been discussed in the context of gamma ray repeaters. For example, in Thomson-Duncan's trapped firewall models. And as I list below, as I listed like this, this has also been discussed in the context of the FRB. Basically, and as I listed, this has also been discussed in the context of FRB model. And so, and what we think in as when in the Newton's magnetic sphere is in a very rough way, what we considered as the Alfven waves are generated by star waves or some magnetic activity on the surface of neutron star, and these waves add energy to the plasma in some dissipated process, and then by some process converted into photons. Of course, there is no consensus on each of these processes. However, how Alfven waves propagate and dissipate in the magnetic sphere is a very important issue. In considering such a scenario, there is an argument to which we should refer. In the context of solar physics, propagation and stability of Alfven wave has been well discussed and obtained some conclusion. According to this research, Alfven waves have an instability called decay instability. This is the interaction of the three waves and in the plasma with a strong magnetic field. Alfven waves decay into slow and Alfven waves. Like this, Alfven waves decay into total Alfven waves and some acoustic waves. This is a promising candidate for a model of corner heating. And since the slow mode, generated slow mode, is compressive, it creates a shock wave, and then shock wave hits the plasma. We have considered such a process in relativistic plasma, relativistically magnetized plasma, such as magnetic sphere. So what is relativistically magnetized? It means that the energy density of electromagnetic field exceeds the rest mass energy density. And the parameters that qualitatively express this situation can be defined as like this. Typically, in the magnetic sphere, the value of this sigma is 10 to 3 or larger. Some people maybe think that if the magnetic field is so strong, we can use a force-free approximation. However, we have chosen not to impose a force-free approximation. The force-free approximation is an approximation negating the contribution of magnetic field. But in this case, the slow wave, which is corresponding to the fluctuation of the matter field, disappears, and the generation of waves leading to plasma heating cannot be discussed. Furthermore, in force-free regime, Alfven wave is stable against three-wave interaction. So, we investigate the stability of analysis, stability of Alfven wave in the plasma with relativistic magnetization without force-free approximation. Okay, let us move on to the detail. As a basic equation, we adopt a special relativistic ideal image equation like this. And key assumption is shown here. For simplicity, we consider parallel propagation only. In this case, slow mode becomes pure acoustic waves, and fast modes degenerate with Alfven wave. Furthermore, we assume that the parent Alfven wave is set to the circularly polarized wave. And we will add a perturbation to the previous equation. First, we have a uniform plasma and plasma with a magnetic field D0, then we then consider the Alfven waves propagating in this clean plasma. The parameter that characterizes the amplitude of this Alfven wave is defined as eta, like this. Then we add more such perturbations to the background field in which Alfven wave exists. Green ones indicate the Alfven wave-like perturbation, and the blue one is like sound wave-like perturbation. Thank you. So what we needed to find is whether this perturbation, do the perturbations grow, is a key question. Okay. What we do is like this. I will not go into detail, but equations for perturbation are thus we can obtain. And these are equations for sound wave. These two are for sound wave, and these two are wave. These equations are linear with respect to the perturbed quantities. So finding a solution is equivalent to the finding a dispersion relation. So let us check there is there any unstable solution in the dispersion relation. So okay, the dispersion relation we obtained is look like this. Here we the number and the wave number and the frequency of the total Alfven wave is rewritten by using the resonance condition to represent the C wave as a single dispersion relation. If we set eta, that means parent wave amplitude equal to 0, and the dispersion relation naturally reproduces the uniform plasma dispersion relations like this. The red one means the Alfven wave forward propagating Alfven wave, and the green lines are backward Alfven waves, and the blue lines are acoustic wave, like this. If we set eta equal 0.1, thank you, we obtain the figure like this. The curves written with blue color indicates it's a stable oscillation solution, and on the other hand, the red lines indicates an unstable growing solution. Okay. What we find is this equation. This equation is the most important our results, and this is a growth rate of this instability, maximum value of growth, this instability growth rate of maximum value of growth rate of in this instability. Instability equation can be written as like this. Then for larger sigma, this value suppresses this growth rate, but although larger sigma suppresses the instability, Alfven waves are still unstable with respect to the decay instability. Okay, this is on my slide. I think that's all. Thank you.
Okay, thank you, Wataru. Any question from the audience here? If not, I have a quick question. So maybe naive question, but maybe this research is kind of purely theoretical. So maybe people here want to understand maybe what is the maybe the direct kind of effect of this decay instability to FRB observation. Could you comment on this?
Yes. By this instability, some sound wave will be generated. So such a sound wave becomes may hit up plasma, and so it may candidate of heating source of X-ray flare or something.
So this could affect the particle acceleration
Yes.
in the magnetosphere, and this will also create a secondary other emission too, not only FRB.
Yes, not. Of course, the coherent emission itself is very difficult, but so I can't conclude that, but may relates.
Okay, thank you so much. Okay, so